Thank you for joining my talk. So today I'm going to talk about open and secure, how the seemingly contrasting things go hand in hand. The most transparent code in the world can hide the most dangerous vulnerabilities. Code that anyone can inspect can still harbor critical flaws. We will walk through to understand what OSS means, what this free stuff really is, have a look at some of the early concepts of security in open source, and see a few real-world examples of how security breaches have happened in the past and how we can manage it. So how many of you, with a show of hands, run open source in the production? Who am I kidding? We all do. For stats, according to the Synopsys OSSRA report, 96% of applications contain open source components. An average application contains around 528 open source components. Docker Hub alone gets 13 million GitHub pulls, image pulls per month. So Linux is everywhere. We all know that. Android smartphones are based on Linux kernels. It powers servers, smart TVs, routers. The whole internet works really because of open source. So whether you know it or not, you are using open source. Let that sink in. This is no longer about whether to use open source or not. That ship has sailed. But how to use it securely and responsibly. So let's address the elephant in the room. What is free software? What does it really mean? When we talk about open source, we're really talking about the 4 freedoms from the GNU definition. That is freedom to run it, to study it, to redistribute it, and to modify it. And because we all use open source, I'm not going to belabor on this. But here's what most people misconceptualize. Does it really? Let me give you some numbers. Red Hat, you know, the company that gives away its code for free. It generated $5.2 billion in 2023. It was all open source. IBM thought that business was worth $34 billion when it acquired Red Hat. So what are they paying for? Well, it's support, integration, expertise, compliance, security patches, someone to call at 3 a.m. when things don't work. The code might be free, but the total cost of ownership definitely isn't. And this is where things get interesting. Not all open source is created equal. There's a spectrum of transparency. Most people don't realize where their dependencies actually sit at. So at level 1, it's available. It's somewhere on the internet. It could be on GitHub or some forgotten FTP server. That's it. On the second level, it becomes accessible. You can actually find it, download it, build it without spending 3 days to figure out what all dependencies are there. On the third level, it is auditable. It's well documented, it's readable, has tests, and a security researcher could actually review it. And on level 4, it becomes audited when a security expert has actually looked at it with a critical eye. And the uncomfortable truth about it is that most of your dependencies sit at level 1 or 2. Maybe at level 3 if you're lucky, but level 4, that's really rare. So when people say open source is more secure because anyone can review it, they're assuming level 4, but you're probably running level 1. That's a huge difference. So let me put this into perspective with a visual. So your application, the code that you wrote, that's about 1% of what's actually running in production. Then you've got direct dependencies, packages you've explicitly added. That's maybe around 10 to 20 packages. And each of those dependencies have more dependencies. So these are transitive dependencies. So that's another 200 to 500 packages. And these packages are something that you never chose, you never reviewed, maybe never even heard of. And all that sits on system libraries. That's another 100 plus packages. The security implication, your attack surface is every single line of code in that tree. You're trusting thousands of developers you've never met, working on code that you've never seen. And this is the Jenga tower problem. You're building this massive tower of dependencies, and you don't really know which blocks are load-bearing. Pull out one critical piece. Maybe it's maintained by one person who got burned out and walked away, and the whole thing comes collapsing down. So we're all dependent on this massive ecosystem of free software that we don't actually review. But wait, doesn't open source have that really famous advantage, the whole many eyeballs makes bugs shallow thing? Let's see that. First, let's get the quote right. So Eric Raymond coined it in his famous essay, The Cathedrals and the Bazaar, that, given enough eyeballs, all bugs are shallow. But here's what most people don't know. Linus Torvalds clarified what it actually meant, that more users find more bugs, not more users prevent more bugs or more users make more code secure. They just find more bugs. And it worked. In 2017, Apache Struts, which is a widely used Java framework, a critical vulnerability was discovered, and within 48 hours, over 200 developers from around the world collaborated on a fix. Patches were released, documentation updated, migration guides written, and problem solved. So that's the power of community when it's actually engaged and coordinated. Fast, comprehensive, effective. And the theory is beautiful, right? More developers means more code review, more users means more bug reports, more testing means higher quality, and all of that leads to better security. It makes sense, it's logical. And here's the reality. We all know about OpenSSL, and if you don't, it's the cryptographic library that secured and still secures about half of all HTTPS traffic on the internet. Banks, hospitals, government systems, e-commerce, everything used by millions of developers, deployed on hundreds and millions of servers. And sitting there right in the code for over 2 years was Heartbleed, a buffer overread vulnerability that could leak passwords, encryption keys, credit card numbers, medical records, and almost everything here. And I would throw this question to the audience. Does anybody know how many people actually understood the OpenSSL code base well enough to have spotted this bug? Anybody? Just throw a number. Guesswork. Well, a 2014 analysis says 12. 12 people out of the millions of users, out of the thousands of developers. And that's not many eyeballs. That's a handful of exhausted experts trying to secure half the internet. This is the bystander effect, but for code review. When everyone assumes someone else is checking for security issues, often nobody is checking for security issues. Diffusion of responsibility at an internet scale. OK, so are things getting better? Actually, yes. The data shows real improvement. CVE disclosure time has dropped from an average of 200 days down to 90 days. And that's a huge improvement. 73% of critical vulnerabilities now get patched within 30 days. Not perfect, but way better than it used to be. Bug bounty programs are there. HackerOne reports a 4 times increase in valid vulnerability submissions. That's more eyes, more rewards, more incentives working. GitHub security advisories have disclosed over 50,000 vulnerabilities in 2023. And Dependabot is now automatically scanning for 40 million repositories. And here's the key stat. 70% of those vulnerabilities were reported by external researchers. That is the community contributing. Despite being the highest value target on the planet, Linux kernel exploits are rare and get patched incredibly fast. So yes, many eyeballs can work when they're incentivized, when they're looking for security issues, and when there's infrastructure to support them. But, and this is important, challenges still remain. 85% of critical OSS projects are maintained by fewer than 5 people. And we've just talked about this, but it bears repeating. Burnout is a real factor. Key maintainers are walking away because of the pressure. It's becoming unsustainable for them. And these are real human beings, often volunteers carrying enormous pressure, enormous responsibilities. The many eyeballs benefit is real, but it's not automatic. It's not evenly distributed either. So if open source has its challenges, what about the alternative? What about closed source? Does hiding your code make it more secure? So imagine you've got a key to a really huge mansion that you own. So where do you hide it so that nobody can find where it is? Right there, under the mat. Nobody's ever going to think of that, right? That's the idea of security by obscurity. I can't see the key because it's under the mat, so therefore it's secure. Not so much. Because the problem with secrecy is that it doesn't end up well. Secrets become known. A lot of proprietary world confirmed with what Gene said. The only truly secure system is the one powered off, cast in a block of concrete, sealed in a lead-lined room with armed guards, and even then he would have his doubts. This perfectly explains the notion of obscurity, and in particular, security by obscurity. And we all know what it means because we've seen examples of this. Remember the DVD copy protection, CSS, content scramble system? The movie industry had spent millions developing it, kept it a secret, claimed it was uncrackable. A 15-year-old Norwegian kid cracked it in 1999. And here's the economic reality. There's a black market for zero-day exploits, professional hackers, state-sponsored groups. They're paid to reverse engineer your software. They will find vulnerabilities. The question is, will defenders also get to see them? With closed source, attackers get knowledge, defenders don't. That's asymmetric warfare, and you're being on the losing side. In 1833, August Kirchhoff wrote down a principle that should have settled this debate 140 years ago. A crypto system should be secure, even if everything about the system, except for the key, is public knowledge. In modern terms, your security should not depend on how something works, but it should depend on protecting the secret, the key, the encryption, the password or the credential. But open source isn't automatically secure because it's open. We need to talk about what happens when transparency isn't enough. December 2021. If you were in cybersecurity at the time, you know exactly where you were in that weekend, the weekend that broke the internet. Let me take you back to that week. Thursday, November 24th, 2021, Thanksgiving in the US. Chen Zhaozhen, a security researcher at Alibaba, discovers something in Log4j. He reports it to Apache privately. Nobody outside knows yet. Friday, December 9th, 2021. 2 weeks later, Minecraft servers start behaving strangely. Players are typing weird strings into chat boxes, and servers are executing code. Someone notices, posts it on Twitter. And within hours, security researchers are investigating. 9 a.m., same day, Friday morning. This is bad. Noon, Friday morning. The same day, this is really bad. And by 6 p.m., everybody's like, oh my God, this is everywhere. On December 10th, 2021, the CV gets assigned, and the CVSS score is 10. Perfect score, maximum severity, critical for confidentiality, integrity, availability, no mitigations, trivial to exploit. That almost never happens, and when it does, you know it's bad. The immediate impact of this was that China suspended partnership with Alibaba Cloud for Log4Shell vulnerability. The CISA issued an emergency directive that hundreds of millions of devices were at risk. Germany's BSI raised threat level to red. That's the highest level that they have. Belgium's CERT called it one of the most critical vulnerabilities of the decade. So what happened? Well, to begin with, Log4j is a logging library. Developers use it to record what happened in their application. So a user logged in, you log it. An error occurred, you log it. But why was this the vulnerability that made the headlines worldwide? Well, four factors come to create the perfect storm. First is the ubiquity. Java runs on more than 3 billion devices. Log4j is in everything. Industrial control systems, network appliances, IoT devices. If it ran Java and did logging, it probably had Log4j. The second one was invisible dependencies. And this is the insidious part. Most developers didn't even know that they had Log4j. It wasn't a direct dependency. It was 3 or 4, sometimes 5 levels deep into your dependency tree. And you never chose Log4j. It just appeared. Let's say your application uses Spring Boot. Spring Boot uses Spring Web. Spring Web uses Tomcat, and Tomcat uses, guess what, Log4j. So the first question that everybody started to ask was, do we have Log4j? And most organizations didn't know the answer to this. The third factor is feature creep. Log4j started as a simple logging library. Write messages to a file, which is basic. And over the years, they started to add a lot of features to it. So there was JNDI lookups, LDAP support, remote configuration, and tons of other features. The security assumption that everybody made while adding these features was that it's just logging. Logging is safe. Nobody scrutinizes logging calls for security implications. You can review authentication code, authorization code, database queries, but logging, that's benign. Except it wasn't. And the fourth factor was maintenance reality, or the imbalance. There were only 3 to 4 active maintainers for Log4j, volunteers, and no paid security team. No resources for comprehensive security audits, and just imagine the responsibility on them. It was a volunteer project. And they've been securing half the enterprise Java world. OK, so we know that it was a nightmare, but here's what's remarkable. We actually tackled and learned from it. One of the first lessons that we learned was SBOM acceleration. SBOM is a software bill of materials. And before Log4j, less than 10% of organizations had comprehensive SBOMs. Today, 60% actively implement SBOM practices. And actually, the US government issued an executive order that if you sell software to the federal government, you must provide an SBOM. And that's not a recommendation, so that's a law. And the shift that we see here is that the industry went from what is an SBOM to show me your SBOM within 18 months. The second lesson is supply chain visibility. So GitHub dependency graph became a standard feature, not an add-on anymore. Other software composition analysis tools also increased 300% in adoption after Log4j. The third lesson that we learned is incident response improvements. Organizations with documented dependency inventories responded 5 times faster. Communication improved. Security teams and developers actually coordinated instead of working in silos. And the fourth lesson is of industry collaboration. OpenSSF committed over $100 million to critical OSS projects. These were engineering resources from Google, Microsoft, Amazon, and the Linux Foundation. These were security audits, sustained funding. CISA created a list of critical open source projects, and government finally recognized that this is infrastructure that we all depend on. The corporate world stopped treating open source like free lunch and started treating it like critical infrastructure. And there's something else that we learned as well. There were systemic issues. So we learned that sustainability is a crisis. Volunteers can't carry this burden alone. Dependency hell is real. Transitive dependencies are invisible attack surfaces, and security assumptions are dangerous. It's just logging nearly broke the internet. Log4j was a wake-up call, and it's been 3 years since. But, 3 years, yeah? 4 years. But the question is, are we still staying awake? So let's break down the challenges that remain. And there are 5 major categories that we need to address. First is the sustainability crisis. So 85% of critical OSS projects are maintained by fewer than 5 people. And 70% of those maintainers are unpaid volunteers. We have essentially built the internet on volunteer labor. And OpenSSL before the Heartbleed had a $2,000 annual budget, 1 developer securing half the internet's encryption. And there was burnout, and maintainers were walking away. We don't have a sustainable funding model for critical infrastructure. And what all this shows us is that it's not a technical problem anymore. It's becoming an economic and a social problem. The second challenge was of expertise shortage. So there's a 3.5 million person gap in cybersecurity workforce globally. OSS security specialists are even rarer. Cryptographers worldwide who are actually qualified are less than 1,000 people, and it takes about 5 to 7 years to develop the real security expertise. You can't just train someone over the weekend. Senior maintainers are aging out without successors, and knowledge exists as undocumented tribal wisdom. New contributors are intimidated by all these security responsibilities. And the third one is of training and mentorship. Even when we want to train a new security contributor, we face obstacles. There's a steep learning curve. Security requires deep technical knowledge plus threat modeling mindset. The experts who could train others are already overwhelmed maintaining the critical projects. And the new contributors see the responsibility and complexity and walk away even before trying. And then we move to supply chain coordination issues, where when a vulnerability is discovered, coordinating disclosure and patches across the entire system is incredibly complex. There's no standardized process. And every major vulnerability is reinventing the wheel. And then we move to legacy system integration challenges. And this is the dirty secret that nobody tells. We've got production systems from 2005 running ancient versions of everything. If it's working, don't touch it kind of mentality. And as we're just catching up with yesterday's problems, new ones are emerging as well. So for AI-generated code and ML model security, the new challenges that we face are, so GitHub Copilot studies are showing that 40% of the AI-generated code contains security vulnerabilities. We're training AI on existing code, which includes existing bugs. And now AI is creating novel attack patterns that humans couldn't even think of. There's cloud-native complexity, organizations running more than 10,000 container images, and Kubernetes misconfiguration is the new vulnerability here. And then there's edge computing and IoT, millions of devices in untrusted environments, limited resources for security tools, firmware with embedded OSS components that can't easily be updated. And everything that we've talked about, the theory, the history, the challenges, it comes down to this, the practical actions that we can take tomorrow. And it could be broken down into a three-phase approach. So let's say you have your own organization and you want to implement security in it. You start with phase one, which is the discovery for the first 2 months. You should know what you have. It sounds obvious, but after Log4j, it proved that most organizations don't know, and it's important. It's important to inventory all the application, generate baseline SBOMs, identify high-risk components, unmaintained libraries, frequent vulnerabilities, and establish an approval system for new dependencies. In the phase two, for the next 2 months, you can integrate dependency scanning into CI/CD, configure automated vulnerability alerts, and implement dependency update testing workflows. In the last phase, you can establish dependency review board, create escalation procedures for critical vulnerabilities, implement license compliance workflows, train the developers on secure dependency practices. And this is a 6-month journey, not a weekend project. But organizations that did this before Log4j responded in hours, and organizations that didn't, they took days or weeks. So that's the ROI, disaster response time measured in hours instead of days. And the bottom line is that security isn't a one-time project, it's an ongoing commitment. The tools exist, the framework exists, the knowledge exists. What's often missing is the organizational commitment to actually implement and maintain these practices. Make security a priority, not an afterthought. Thank you.
Thank you, Nikita, for a nice talk. I'm wondering, for some of the vulnerabilities you mentioned, like, for example, Heartbleed or Log4j, if you have some ideas of maybe how to prevent those, rather than just reactively try to see when we find them, let's try to patch as quickly as possible.
So I guess in the practical recommendations that I gave, which is like a long project, if we already have those information about at least what all dependencies we do have in our project, it could become a bit faster. But it's like if you don't have a prepared system before, it's going to be like a last-minute thing with every vulnerability that you get. So being prepared is better in those cases.
Anybody else? OK, we'll wrap it up there. Thank you very much, Nikita. That was great.
Thank you.